So I'm not actually a mathematician. I'm a physicist, but I started off as a mathematician. And actually, when I studied in the mid-90s in Moscow, I was not at Moscow State University. I was at Moscow Institute of Physics and Technology, MIPT. But I actually was at the time doing theory of functions. So I was attending lectures in the same department where Azad was doing his studies and was doing his PhD. So I feel a lot of affinity with Azad and with his mathematics and with his very courageous actions because as his wife said, he made. He was part of this group of people who realized that that something needed to be done about this Putin regime, while many of us were still trying to play kind of an ostrich game and trying to think that we can outsmart, we can still do something useful with, while being ambivalent about this regime and trying to, be a little bit of on some things to collaborate with this regime. And clearly, this strategy of appeasement, it led in particular to the disaster to this war, which Russia started against Ukraine. And at that point, even though this war has started already 8 years ago, and there was a big sense of injustice, but I think after 24th of February, even the most ostriches among us couldn't bear it anymore. So this was really, the most blind people are somehow had their eyes unblocked at that point. So I really hope that we will talk a lot tomorrow also about what to do about all this, how to the long-term strategy of how to bring freedom to Azad and to all political prisoners who are whose numbers grow by the month, by the day in Russia. And is it now 1,000 political prisoners, 2,000 political prisoners? It's more political prisoners now in Russia than it was at the end of the Soviet Union. So what are we going to do about all this, and how are we going to stop the war? How are we going to bring about freedom back to Russia? So actually, when I was a student in the 90s, it was the time of the Chechen War, the first Chechen War in 94. And, it was, I'm telling some of my younger colleagues that at the time there were real debates in the Russian Duma, which we were watching on TV in our student hostel room, with some people being pro-war, some people were against the war. I remember very, very well that Gaidar was against the war, and so there was real political debate, and it's shocking to the new generations to know that at the time in '94, people were actually watching the debates in the Russian Duma, because who now watches the debate in the Russian Duma? Who just prints the whatever is sent down from Kremlin. Yeah, so definitely when we were coming of age in the mid '90s, me and my friends, it's not the kind of future, idealistic future that we were imagining for our country. So these are tragic days. So I'm not really, I don't really have a very big heart to speak about science, but I guess we have to. That's what we do. So that's where we can partly find some solace, if there is any solace. And also, as I say, I'm a physicist, so I'm not a mathematician. So whatever I'm going to tell you here is certainly going to look very strange for many of you, and so I'm not sure how much of you are going to bear with me. Well, I wanted to discuss here two problems, one in physics, one in mathematics. So physics problem has to do with critical phenomena, and mathematics problem has to do with some results about eigenvalues of Laplacians on hyperbolic surfaces. So I have many slides, definitely too many slides, but my point here is that I would like to try to make a point, the philosophical point about certain parallels which these two problems have, and certain conclusions that one can make about, concerning methods that one can approach some problems in science which are not exactly solvable. So let me try to tell you this in some detail. But please, since I'm not one of you guys as far as mathematics is concerned, so you have to interrupt me because I'm not even sure that I talk your language. I could be very bizarre things from the point of view of mathematics. So please pose questions, interrupt. So in these problems, the common features of the problem is that there's going to be a certain Hilbert space at play, and this Hilbert space is going to have a grading by real numbers and some product structure. So basically, there's going to be some orthonormal basis in this Hilbert space, and to each element of this basis is going to be associated a real number, delta I. And I can take products of these elements of this basis. There's going to be some product map, and I can expand them back into the basis. This is supposed to be convergent Hilbert space expansion. And so I can express this coefficients Ci, J, K of this expansion as just the inner product of Vi, Vj, and Vk. So these are going to be the two basic features of both problems, and they're going to be a bunch of extra structures and consistency conditions. And in both cases, there's going to be a certain group which is going to act on this Hilbert space. And our goal is going to be to learn about this delta I's andCijk's. There's going to be certain interplay between these numbers. And in principle, there's going to be a definition of this Hilbert space V, and if you use this definition, you could just compute these numbers. But you cannot compute them exactly because these problems are not exactly solvable. And so instead, I'm going to argue that one can reach some interesting conclusions by relying not on the definitions, but by careful analysis of consistency conditions. So I'm not going to solve the equations. I'm going to derive various inequalities on various parameters of interest, but these inequalities sometimes are going to be surprisingly sharp. And this goes under the name of Bootstrap. So this Bootstrap equation, which is a weird name, so it just says that, okay, since my product is assumed associative, I can, the Vi, Vj, Vk has to be equal to Vi times Vj, Vk. And now to study this condition, I'm going to take an overlap with some other vector Vl. And this has to be an identity for any IJKL. And so this, in my line of business, this is written as this equation, kind of a weird equation, this graphic form. And the reason why it's called Bootstrap is that because depending on your perspective, what I'm going to show you, it may look a little bit miraculous, because I'm basically going to be getting out results out of nothing. And there is an expression, in English expression, that to do something miraculous means to pull yourself by your own bootstraps. So that's the name of this term, which appeared in physics many years ago in the 60s. Okay. So any questions so far?
No, it's fine.
So the first problem with the mathematics problem is going to do with something very, very classical. I'm going to take a compact Riemannian manifold of some dimension d, and I'm going to study the eigenvalue equation for the Laplace with trimary operator on this manifold. So there's a certain spectrum of eigenvalues. There's a minimal eigenvalue, which is 0, constant function, and then there's some discrete spectrum of eigenvalues going to infinity. And in this problem, so I'd like to learn about the eigenvalues. To put this problem in my general form, I'm going to take the Hilbert space in this problem is naturally L2 on X. The grading is provided by the value of the eigenvalue, so they have a natural grading of this Hilbert space. And the product is just the pointwise product of two functions on my manifold X, which is not defined on the full V, but is defined on the subspace, on the dense subspace of, say, C infinity functions on X. That's going to be good enough. And, for example, all eigenfunctions themselves are C infinity functions, so I'm going to have this sort of expansion. Phi I, phi j, the pointwise product can be expanded again into phi k's. And the coefficients of this expansion are just given by an integral of the product of three functions over the manifold. These are called triple overlaps. And so this problem of finding eigenvalues and triple overlaps is not exactly solvable, except on very symmetric manifolds, such as the sphere or the torus. If you are given your favorite manifold, you can go ahead and solve the equation numerically using, say, finite element method, and you can get results with very good precision. So here, I would like to advocate a bootstrap approach that I can learn something about eigenvalues without solving this equation numerically. And so the idea is, as I said, I'm going to consider this quadruple product, which in this case just the product of four eigenfunctions, ijkl, integrated over the whole manifold. And as I said, the double product can be expanded again into the eigenfunctions. So I can, for example, take these two eigenfunctions, expand their product, take the other two eigenfunctions, expand their product. I get an expansion. The eigenfunctions are orthonormal, so I get this series of overlaps,Cijr, Crkl. But I can do this in the opposite order. For example, I can take phi I, phi L, and phi j, phi k, and so I get a different series, which has to sum up to the same number. And so clearly, this is some sort of non-trivial consistency condition, which says that the triple overlaps cannot be arbitrary. There's some. But this condition, so far, it does not involve eigenvalues themselves in any way. You can derive some consistency conditions involving eigenvalues if you consider quadruple products involving derivatives of phi's. And at this stage, it actually helps to get some interesting constraints. It helps to make some additional assumptions on your manifold X. And okay, there was some work. I'm going to talk about some work, but all this work has been in the theoretical physics literature in the recent years. And so I'm presenting things a little bit not in the historical order, because in fact, what came first in theoretical physics was this conformal bootstrap for critical phenomena that I'm going to talk about in the end when I get to this, if I get to this. But okay, but this, as you will see, is going to look a little bit strange. So people started looking for some simple toy models for this conformal bootstrap, and they came up with this bootstrap for eigenvalues. And there might be some work in the mathematics literature, which is related, but these recent developments, they came from the theoretical physics side. So here, theoretical physicists are playing on mathematicians' turf. So and try to do something rigorous. So, okay, there's a bunch of assumptions that you can make, but the work that I'm going to focus on today is kind of the strongest assumption that we are going to go to 2 dimensions, and we are going to consider hyperbolic 2-dimensional compact surfaces. So this is a classic problem. There's a lot of mathematics work about eigenvalues of Laplace-Beltrami and hyperbolic surfaces. So what can possibly poor physicists say new in this classic problem? So we will see. Or maybe you're going to tell me that it's not new. But I'm going to mostly be based on this work by Kravchuk, Mazach, and Paul, which I like very much. So I'm going to explain this work as much as I can. So we are considering a closed hyperbolic surface, which is, of course, going to be a left quotient of the upper half plane by some discrete subgroup of PSL to R. So this you know very well. And so because of this, instead of solving the Laplace-Beltrami equation on the surface, I can solve it on the upper half plane, and I can impose that my function f has to be invariant with respect to the right shifts by the element of this group gamma. Of course, we also have that the upper half plane is the right quotient of the PSL to R by the maximally compact subgroup SL to R. Okay, and so the main idea of this paper, PKM, was that instead of considering the Hilbert space as L2 on my surface X, which is this double quotient, they decided that they're going to work in a bigger space. So they're going to work in a space L2 where you just quotient the group G on the left by gamma. So it's a bigger space, and the reason why they decided to work in this space is because this space carries a unitary representation of G acting on the right. And so now you start deriving various algebraic constraints of what kind. So we have all sorts of group actions. So for example, we have the action of this compact subgroup K on our space V. And under this action, we can decompose V into the direct sum of Vn's, where N is just the Vn is the subspace on which K acts by multiplying by e to the in theta. And so here you see that if we specify to n equals 0, then V0 is, so the set of elements of V which are invariant under this action of K. These are precisely the functions on the surface X. So this is what we really want. And all the other things, Vn, they transform under they transform as n forms on X. And so this construction, it nicely combines functions and forms on the surface into one bigger space on which the group G acts unitarily. But as I said, we also have this decomposition of our space V under the action of G. So this is unitary action of G, and so under this action, there's going to be some decomposition into unitary irreps of PSL to R of our big space V. So which representations are going to occur, we don't know. So this depends on the surface. This depends on gamma. But all representations, they have to fall into this, the usual list of irreducible representations. So this is going to be either the trivial representation, it's just a constant function. Okay, then there is principal and complementary series. And actually, for this story, I'm going to put them together. So I'm going to bundle them all up together as I'm going to call them P lambda, where lambda can be either in the range lambda larger than or equal to 1/4 or between 0 and 1/4, and lambda is related to the usual label delta that one uses for these representations by this formula that lambda is equal to delta times 1 minus delta, which is the value of the quadratic Casimir. And the reason why I number them by lambda is that because this lambda is precisely the eigenvalue of the Laplace-Beltrami operator. So for every representation of this type P lambda, there exists one vector V delta, which lives in the V0 part of P lambda, which is an eigenfunction of Laplace-Beltrami with eigenvalue lambda. So if I want to learn something about eigenvalues, I have to learn which of these P lambdas are going to occur in the decomposition. And then finally, there are these discrete series representations, which are related to holomorphic modular forms on my surface X. And the nice thing about them is that by the Riemann-Roch theorem, I know precisely how many of them are there. So now the game that we are going to now play, we are going to pick a quadruple overlap of 4 holomorphic modular forms. So here, there was this game that I explained here that we were taking the quadruple overlap of 4 functions, and I was expanding it in 2 different ways. So the game that these people, Kravchuk, Mazach, and Pal came up with is, so they said, we're going to take 4 holomorphic modular forms. We know that they exist on every surface in a certain number. And now we are going to take the tensor product of representations to which these holomorphic modular forms belong. And if I take the tensor product holomorphic times anti-holomorphic, I'm going to, in this tensor product, I'm going to discover representations which are of this principal plus complementary type. And so I'm going to learn something about the eigenvalues. While in the other channel, when I take the product holomorphic times holomorphic, then I'm going to again get representations of this discrete series type. So I'm going to again be operating with this, with the holomorphic modular form world where I know what things look like. So is this, how is this going? Are there any questions?
Fine, I don't see questions, so it's fine.
Well, that's what I'm worried about, because if I have questions, it might mean that. So, of course, this group action, it plays a huge role in all this story. So when I take a product of 2 smooth vectors, decompose it into irreducibles, then the way this decomposition depends on the vectors I started with is completely fixed. Well, not completely, but it's fixed by gene variance to a huge extent. So the space of such gene variant maps is at most 1-dimensional, and it's known exactly, where this map exists, where it does not exist. So I hope that the idea is clear. So perhaps I can fast forward to this equation. So you start with 2 holomorphic and 2 anti-holomorphic modular forms, where these are just some vectors in your, these are just some smooth vectors in your Hilbert space. Now, you don't want to work with just one form. You want to work with the whole, you want to have a family of vectors which belong to the same representation in which the form lives. And so there is a nice way to construct this holomorphic family of vectors, depending on the parameters W, which lives in the parameter W, which is a complex number in the unit disk. And similarly, If you do an anti-holomorphic form, then you take this parameter W in outside of the unit disk. So these extra parameters, you can choose them whatever you like, and they give you access to a dense set of vectors within these representations, within these discrete series representations. And at the same time, by G invariance, you know that this function, which depends a priori on W1, W2, W3, W4, in fact, you know that it depends not individually on these W's, but it depends on them through this cross ratio zeta, which is a conformally invariant cross ratio. And on top of that, you know that, as I said, we can now use this product structure. We can take this product of FF and we can decompose it in the irreducible representations. And if we do this, we are going to find that this function f of zeta, which is going to be given the following expansion. So it's a series which goes from P equal 2s to infinity, because the holomorphic forms which can appear in this decomposition, they start from weight 2s. Then this coefficient Cp squared, you don't know what they are. So these are some triple overlaps of three holomorphic forms. So if you knew what the holomorphic forms are, you're going to do the integral, you know what they are. But here in this approach of KMP, you say, okay, I'm just going to use the fact that here I have some coefficient, which is a non-negative number. And finally, here you have another function, which I call here GP of zeta. So this function is completely fixed by G invariance. So you can just compute this function. It's just some 2f1 with certain weights. So it's just a matter of computation to find this function. And then you can do the same computation differently. You can take the product of holomorphic times anti-holomorphic. And here you are going to get, in the tensor product, you're going to get the trivial representation, and you're going to get the principal plus complementary series representations. And if you do this, you get this expansion, which is an alternative expansion for the same function. And again, you have some unknown triple overlaps of holomorphic, anti-holomorphic form and the Laplacian eigenfunction. And again, you have some group theoretic function that you are supposed to compute. And again, it's some hypergeometric function. So this thing is known in physics as the Bootstrap equation. So it's some equation which is a sum. It's an equality of two sums with unknown but non-negative coefficients. And also, you don't really know which functions occur here. Well, on the left-hand side, you know that you're going to have functions occurring from 2s to infinity. On the right-hand side, you don't really know what these delta i's are. In fact, we would like to learn what are the delta i's which can occur in the right-hand side, consistently with the fact that the function has these two expansions. And okay, and so believe me, but what now these people did is that they took this expansion, and now they did this very elementary effect. They just expanded this equation at small zeta. So you set all the Taylor coefficients to 0, you get infinitely many constraints. But okay, let's just look at initial finite subset of constraints, which are like order 10 constraints. These delta i's, they enter into these equations as just some algebraic coefficients, because when you expand the hypergeometric function, you're going to get this delta i's, or their combinations lambda i's all over the place. Now you can ask, for which lambda i's can I satisfy this equation? For example, let me suppose that all lambda i's, all Laplacian eigenfunctions, all Laplacian eigenvalues are just, ridiculously high. I don't know, larger than 1,000,000. Is there a solution to this equation? Well, then you very quickly convince yourself that no, this cannot be the case. So this equation only has a solution if at least one lambda I is sufficiently low. And so now you can start to play more quantitative games. So by playing these games, so the games enter, so now you can try to input the genus of the surface. So through the genus of the surface, you know how many holomorphic forms are there. So here I was talking just for one holomorphic form of certain rank S, but we can, if there are several forms, then you get more complicated, more constraining equations. But if you just take genus 2, then there is one form for sure. And by using this equation, they managed to derive, this KMP managed to derive that the first eigenvalue has to be bounded from above. This is a rigorous result from this equation, just using about 10 of these equations, by this number 3838897, blah, blah, blah. And it actually turns out that this number is extremely close to the known first eigenvalue for the Boltzmann surface, which is conjectured to have the maximal lambda 1 for genus 2. So, depending on your perspective, this may look miraculous because I'm not putting here, Boltzmann surface is some particularly very symmetric surface, a certain symmetry group. I'm not inputting here anything like this. I'm just inputting very general constraints, should be true for any surface. And yet I get that the maximal eigenvalue given this equation comes out very close to this Boltzmann surface. And perhaps if instead of using 10 constraints, I would use 20 or 30 constraints, maybe I would get even exactly to the Boltzmann surface answer. This is not known. And you can repeat the same thing for the Klein quartic, for genus 3, and again, it works. So that finishes my example of mathematics example. So for you to judge how miraculous this is, what to do with this, if this is competitive with what mathematicians know how to do, but that was all concerning the math example. So if you have any questions about the math example, then please ask before I go to physics.
I don't see questions. There is a question. So, Offer, you can ask your question.
Just go back to what was delta in the capital, in the equation. You had capital delta. Was it the eigen?
So lambda was equal to, eigenvalue was lambda, and lambda was equal to delta times 1 minus delta.
Okay.
So delta was really the label of the representation.
Okay, now maybe I don't know the prerequisite, but in this, so is it known? I mean, that you said it is a direct sum of irreducible representation. Of course, not every unitary representation is a direct sum, but here it is known because this is a general result on automorphic forms or something that it is
Well, yeah, it's a very particular unitary representation on functions. So I guess in this case, it's known that it is a direct sum. But I wouldn't be able to.
With finite multiplicities or.
Yeah, I hope my colleagues whose work here I present, they check this carefully.
No, because I know that in number theory, like when you have automorphic representations, so the kind of the cast forms gives a direct sum. anyway, I don't know. It should be just some general thing.
This should be some general. It's a very benign representation. So
okay, I don't know the.
Yeah.
And of course you have all this infinite thing, so that the equations are always some infinite. Of course,
yeah, there are infinitely many. There are infinitely
you have some
many
convergence properties of
yeah,
this.
yeah. There are some You have to establish convergence. So again, this is established in this paper. So this is actually a rigorous paper that I'm presenting. It's written as a rigorous paper with theorems. And even this bound that I derived, they first. I mean, they derived it numerically, but it is some rational arithmetic, so it's a rigorous bound.
Okay, thank you.
So okay, so let me go to something much less rigorous, which is in physics. So I'm going to talk about three-dimensional Ising model and critical phenomena. So that's what is related to what one of the Fields medals was awarded today. And so the three-dimensional Ising model is a spin lattice model on a three-dimensional cubic lattice, which you can take infinite, or you can think of it as a limit of a finite lattices as you increase the size. There is a certain partition function. There is a certain interaction of neighboring spins. It's a Gibbs distribution. I'm considering just the simplest case, nearest neighbor interaction, spins plus or minus 1. So this is the two-dimensional picture, but imagine putting things on top of each other, so it's a 3D picture. And so in this problem, the people are interested in these numbers, called also deltas, as in the previous problem, which appear as exponents of power laws of correlation functions. So you take two spins, which are very far away from each other, and if you tune the temperature to the critical temperature so that you get the phase transition, then this spin-spin correlation function is a power law. And the scaling dimension, this delta sigma is called scaling dimension. It's not known exactly what it is, because this three-dimensional Ising model is not exactly solved, and it's believed to be not exactly solvable, unlike the two-dimensional case. But one interesting thing is that this number delta sigma, it's believed to be universal, in the sense that it doesn't really depend on the model you start with as much. So if, for example, you take the model, so this model, Ising model, has this property that if you flip all the spins, you change the sign of all the spins, then the partition function doesn't change. So this is what we call Z2 invariance of the model. So let's keep this property, but let's change other properties. For example, we can change the lattice. Instead of taking the cubic lattice in 3D, let's take some other lattice. Or we can add some other interactions to the model, allow spins to feel not the nearest neighbors, but also next to nearest neighbor. It is believed that this number delta sigma is not going to change in this case. And these beliefs are supported by experiments, by Monte Carlo simulations, by non-rigorous realization group theory due to physicist Ken Wilson. And so there is hardly any doubt that in the physics community that this is true, but this has not been yet proven mathematically. And in fact, one can pile up kind of more highbrow mathematical conjecture on why, if this delta sigma is so universal, then there should be a certain universal mathematical object which captures it. So what is this object? And so this object goes under the name of Euclidean field theory. So it's this Euclidean field theory, it's a probability distribution, probability measure in the space of distributions on R3. So we kind of imagine that when the lattice goes away, everything is in the continuum. So we have a certain field sigma of x, but this sigma of x is not a random function. So the spins were random. So what represents them in the continuum limit should also be a random thing, but it should not be a random function because there are some singularities when you take this continuum limit. So it should, at best, it could be a random distribution. And you can still talk about correlation functions of these random distributions because these are related to the moments of this probability measure. So we can still talk of this correlation function sigma x1, sigma xn, and these things, they should be real analytic functions as long as all these points x1, xn are different from each other. But if the points collide, then this is perhaps a distribution. So there are some singularities. And so if you go to field theory, then in field theory, the 2-point correlation function sigma x1, sigma x2 is just a basic power law, 1 over distance to the power 2 delta sigma. While, as I said, if you go to the Ising model, then in the Ising model, these 2-point correlation functions of two spins, so spins are not continuum objects, they just take values plus or minus 1, then this goes as 1 over r to the delta sigma as long as you go to large distances. And so the conclusion of this discussion is that this Ising model that many people know and love, it's nevertheless a very dirty and non-unique beast. So at the critical temperature, if you go to the critical temperature, then it becomes a little bit less dirty because at high distances, you have this universal power laws appearing. But at small distances, there is still a lot of dirt. So what you do is that when you go to this field theory, then you acquire finally this maximally pure mathematical object which should capture universality. And this object, it has a lot of symmetries that the lattice model doesn't have. So it should have exact scale invariance, exact translation invariance, exact rotation invariance. And finally, it's believed also to have conformal invariance. So it's, if you take this field sigma of x and we rescale this field, we reparameterize this field by a conformal map, and we also multiply it by some x-dependent factor depending on the Jacobian on this map, then this probability measure has to be invariant. And since this rescaling factor, it specifically depends on delta sigma, this explains why this delta sigma is universal, because this conformal field theory, it should exist only for this delta sigma, but not for other delta sigmas. So that's kind of a highbrow conjecture, which has not been mathematically proven. But okay, what can we do with this? So here I explained a bit about conformal transformations of R3, but I presume you don't know this, so let me skip this. So the point is that in this problem, we can assume that this field theory exists, and then we can try to find in it with this structure about the Hilbert space and the product and everything that I was talking about, and then we can write down a Bootstrap equation, which is going to be a consistency condition. And then by solving this Bootstrap equation, you can hope to put some bounds on this delta i's, which are experimentally interesting quantities. So you can, for example, you can take a magnet, you put it at critical temperature, then you scatter neutrons on this magnet, and then you can measure this delta I, this delta sigma exponent. You can measure it. It's experimentally known with good precision. Or you can also measure heat capacity of water at this critical point, and you can also measure this. There are many ways to measure this exponent. And so the point is that if you take this random measure, so as I said here, okay, sorry, I skipped this. It's good to see, since conformal transformations, they best act on the sphere, not on the d-dimensional Euclidean space. It's best to assume that we live on the sphere as d equals three dimensions. So, and when we restrict this probability measure on fields which live on the equator of the sphere, then you get our space of states, which is which is an L2 space on distributions living on this equator. So it's some pretty wild beast. And because of conformal invariance, if you, instead of doing this, you restrict fields living not on the equator, but on some small sphere, smaller sphere, then you get the same space. So there is some isomorphism between the two spaces. And again, because of conformal invariance, you have the action of the conformal group on this space. And finally, this product structure, you have this, you can say that I can also consider transition amplitudes where I can put I can glue in a state V1 to this equator, well, not equator, some small sphere here, V2 and here Vn, so I can take arbitrary number of insertions. And so for people who are familiar with Segal's axioms for two-dimensional CFT, this may look familiar, that something like that could work also in the three-dimensional context. And finally, so we have this grading. So as I said, we have, so I talked about this field sigma, which has scaling dimension delta sigma. But in fact, what happens is that this whole Hilbert space V, it can be decomposed into irreducible representations of the scale transformation generator D. And delta sigma corresponds to just one of these representations. Well, let's call, okay, delta 1 is some trivial representation, delta 2 is delta sigma, but there are going to be infinitely many other representations appearing in this decomposition. And so this means that in fact, our theory, in addition to this field sigma, it has other fields, or as we say in physics, operators, OI, which come equipped with their own scaling dimensions delta I. And so we can, by following this line of reasoning, we discovered that we should discuss not just the correlators of sigma, but also correlators of other fields inserted at different positions. And because of scale invariance and conformal invariance, the two-point function of fields y and j is just 1 over the distance to the power 2 delta I. So these fields, these extra fields that I discovered using this reasoning, they have a certain meaning in the three-dimensional Ising model as well, but let me skip this. So there is one particular operator, delta epsilon, which kind of, you could think about it as a product of two nearby Ising spins. So we have the field sigma kind of corresponds in the continuum limit to the single spin Si. But if you take the product of two nearby spins, you're going to discover this operator delta epsilon. You can also measure its dimension on the lattice using Monte Carlo simulation, so it's known. And finally, there is this overlap. We were talking about this overlap constants,Cijk, and here they appear by considering a three-point correlation function of three fields y, j, k, and so this is known from some old work by Polyakov that this is proportional to a constantCijk, which is a theory-dependent constant, and the x dependence is fixed completely in terms of the scaling dimensions of the three fields, delta I, delta j, delta k. And with all this formal baggage that I introduced, I can finally explain that there's a bootstrap equation in this game. So I consider a correlation function of four fields, y, j, k, or l, and this I can think by inserting four fields on the sphere. I can cut this sphere along one equator or along another equator, and I can, by doing these depositions, I can express my correlation function in two different ways, and as two infinite sums convergent sums. And again, you see here products of these triple overlaps with an infinite sum about the intermediate state R, and also in the right-hand side, it's in the opposite order. And there are these functions G, which are again completely fixed by conformal symmetry. So just like in this problem about Laplacian eigenfunctions, there were these functions which are fixed by conformal invariance. Here as well, you can work out these functions. And so we don't really know if this whole thing exists. It has not been mathematically proven if this conformal field theory exists, if this random measure in the space of random distributions exists. But if we know that, if we assume that it exists, then we can get to this bootstrap equation, and now we can try to use it to put constraints on the allowed values of delta I andCijk. So that's the idea of the conformal bootstrap. And okay, so basically I just would like, since I'm running out a little bit of time, I just want to say that using this approach in the three-dimensional Ising model, which has infinitely many of these operators, but there are two main operators, which is sigma, the one that I talked about a lot, and epsilon, which is this other operator, which I also briefly mentioned. You can show using numerical algorithms by analyzing this bootstrap equation that these dimensions delta sigma and delta epsilon, they cannot be arbitrary. They are forced to live in this extremely small, in this tiny island elongated shape here, which is marked by bootstrap. So this is really like we determine these dimensions with 5 or 6 significant digits, which is a big deal in physics. It's rare that one can do three-dimensional stuff with such precision. And you see that if you do things by Monte Carlo directly from the Ising model, you get consistent results, but Monte Carlo is difficult, is much more difficult. So bootstrap approach in this problem wins with respect to Monte Carlo. And so this basically brings me to my conclusions. So to my point that I was trying to make, which is that often in theoretical sciences and mathematics and physics, we focus on our attention is drawn to exactly solvable integrable examples, because often we think that, okay, whatever is not exactly solvable is going to be probably chaotic. It's hard to do anything there. But here, or perhaps you cannot say anything analytically, you should do some direct numerical computations from the definition. And in my examples, I showed that sometimes you can do this consistency conditions analysis, which can be quite competitive with such numerical, direct numerical computations. And so it would be interesting to find more examples where this philosophy is useful, and also to understand better why this philosophy is successful in the examples where it is successful. So, so I'd like to stop here, but I'd also like to remind ourselves that we are having fun here, but with science, but people are in prisons in Russia, people are under the Russian bombs in Ukraine. This is very tragic, and we should come up with some way to do something to the best that we can. Thank you.
Thank you, Slava. Thank you for your inspiring lecture. So we have, I think, few minutes to 1 or 2 questions, if there are questions. So please raise your hand. Yeah, so Ofer has a question.
So just a basic question. I remember from some expositions that in physics of this quantum field theory, you have operator value distributions on usually on Minkowski space. But here you said something else. I don't remember you said that you have a random distribution sigma, but then you had some O of x, which can you make precise what is this? A random. This means you have a probability space, and somehow the sigma of f is a random variable.
Yes, that's what I wanted to say. So there are two ways to view quantum field theory. There is a Minkowski approach, and there is a Euclidean approach. They are both completely classical, completely accepted. So in the Euclidean, in the Minkowski approach, you are totally right. You have operator value distributions, and in the Euclidean approach, which is more rooted in statistical physics, you really do probability theory. You start with some probability distribution, be that a lattice model of spins or maybe some lattice-sized field theory, where you take some field action and you discretize it on some lattice and so on, and then you try to take a continuum limit where this goes, the lattice spacing goes to zero. This is often simpler because in Euclidean space, clearly the singularity structure is much easier. You only have singularities at coincident points, while in Minkowski space you have singularities on light cones. So even if you are interested, if your interest is only in Euclidean, suppose you're a statistical physicist, then you can, in the first approximation, forget about this Minkowski space and just work with these random distributions.
And what is O of x before? You had O, after a while you had O, you take correlation function of some other things called O.
O of x. So O of x, in this language, O of x should be some function of the distribution sigma. So it should be some function of sigma. It's not an independent random object. It's some function of sigma, which is defined in such a way that its two-point correlation function is also scale invariant.
So it is again a random distribution.
Yeah, it might not be a random distribution because, generically it's going to be a random distribution as well, but not an independent one. So sigma is kind of the fundamental one, which defines the theory, and all these other distributions, all these other local operators OI, they are functions of sigma.
But why you say operators?
It's just a jargon.
Okay. So I think, I see another question. So maybe just quickly.
Sorry. So I'm curious about whether the machinery, this type of machinery, not necessarily maybe the Bootstrap, but more broadly, this type of machinery used to study Euclidean field theory can be used to study a sort of specific random distributions rather than sort of the general classes like you did with the hyperbolic manifolds. So like if you know, I guess the analogy would be, you give an example where you can figure out something general about Laplacian eigenvalues for hyperbolic surfaces, and a result you get from that happens to sort of match, it tells you something about a specific surface, the Bolsa surface, because that one happens to be maximal, but you can't necessarily say things, or at least you didn't say things about surfaces with like a specific fixed symmetry group. So I was curious about whether in general you can say things about, let's say, hyperbolic surfaces, or more broadly about random distributions where, like, let's say the symmetry group is fixed.
Yeah, I think you can. Yeah, it's for example, I actually already used this implicitly when I analyzed the Ising model. So the fact that the Ising model had Z2 invariance, and so all fields of the model, they were classified by representations of Z2. It means that when I consider this 3-point correlation functions here, like here, then I'm only going to consider 3 fields such that the tensor product of 3 representations of Z2 contains a trivial representation. So they either have to be all Z2 even, or 2 have to be Z2 odd, and 1 has to be Z2 even. So this restricts the possible products already that I have in my theory, and this has been used in the analysis, in fact. So if you have some richer symmetry structure, so there's always conformal in this business. There's always the conformal symmetry, and then there may be some other symmetries on top of it, and which may be in a direct product with conformal symmetry, or maybe some more non-trivial algebraic extensions. And in this case, the whole formalism has to be enriched to allow for this extra symmetry structure. And always, once you do this, you discover stronger constraints because you are now focusing your attention on a subclass of objects.